Welcome back, ladies and gentlemen. We're going to be talking about parallel circuits and considering a couple basic relationships for these guys. We're going to try to answer this question: how do voltage, current, and resistance work in parallel circuits? And so, well, basically we have to understand what parallel means. So if you have a voltage source, let's say it comes out here, and the current will flow out of the positive end of the voltage source. And from there, the current is going to have some choices to make. Some of the current might be able to go this way and go through this resistor. Some of the current might be able to go this way and go through this resistor. And some might be able to go this way through that resistor. But then these things have to all end up going back to the voltage source. Oops, a little too excited on the line. So these are what are called parallel connections. So some of the current flowing toward this spot right here. There's current. Some of it will go through to the left pathway, and some goes through the middle pathway, and some will go to the right pathway. But then they rejoin down here, and the current will flow back toward the battery. I'm going to redraw this so we have more room, and we're going to look at this, but there's something else going on. These locations here and here are important locations. They're called junctions. Right there. And basically that is where wires split, or where wires come together and rejoin. First the redraw, and then we're going to look at what we can figure out. We have a voltage source, and we have, so here's the deal. I need some junctions, and it's could look like this. I mean, it could redraw this, but I'm going to change the way it looks. The thing is, it's going to be effectively the same thing. I'm going to have a junction there. Come down, I'll have a resistor. And there will be a junction here as well. And what I'm able to do is add another resistor. And so you can see wires right here split and wires right here rejoin. But I want 3 resistors in this example. So I'll have a third pathway, third option for the current, right? So I'm going to end up redrawing this one more time in just a minute, but check this out. Okay, I'm going to use this guy. We have some current flowing out of the voltage source, so I'll call this the current from the source. And this current from the source is going to head toward the junction. There is some current headed into the junction, so current in to that junction. And some of the current goes down this way. There's current out. And some current goes this way, and there's current out. And the crazy thing is, well, this current out ends up going toward this junction. And some of it gets split, and there's an output there, and there's an output there from this input. Now, it's going to get real crazy if we try to focus on all 4 of those junctions. We're going to have too many things to talk about, so that's not quite how I'm going to do it. Instead, I want to be able to talk about R1, R2, and R3. Let me label those. That's supposed to be a 1. And I have a voltage source here. So we can recognize that the current splits at the junctions, and some of the current flows through R1, and some of the current flows through R2, and some of the current flows through R3. And the currents, after they flow through these resistors, they rejoin, and then rejoin again, and go back to the source. So let's set this up proper. Quick redraw. Voltage source. Sometimes it's easier to draw the furthest one first, but that's not going to be R1. There and there. R1, R2, and R3. Okay. So there's several things going on. First, let me label that we have a voltage of the source here, and I could measure that across the source. Cool. Each resistor will produce a voltage drop. If the source is a voltage gain, so we have a voltage drop at each of these. So here's a voltage drop of 1, voltage drop of 2, voltage drop of 3. And represent measuring these voltages by drawing them like this, right? Okay. Connection. Now, I also want to represent the current. So, current flowing out of the source. I'll just wrap this arrow around the corner. Current flowing through the source, or from the source, right? And some of this current splits and goes through R1. So we have current through resistor 1. And what doesn't split off and go down here will continue this way. But from the amount that continues this way, some splits off and goes through R2. That would be current 2. And the remainder goes this way and travels through R3. That would be current 3. And what's crazy is this. Well, if you watch how they recombine. This down here, the current is the same along any single pathway, so it's all the same I3, I3, I3. Oops, not I3, because now I2 is joining it. So right here, you could say, well, you've got current of 2 and 3 combined. Really, you got the same thing up here. This is current of 2 and 3 combined also, because it splits into 2 and 3. And as current of 2 plus 3 combined gets here, current from 1 is added to it. And so there's a current here going back to the source, and this is really 1 plus 2 plus 3. But think about this. It's current through the source. It's that. So this is crazy. Well, I'm going to do the 1 and the 2 and the 3 there. But that is equal to the current of the source. Interesting. So what, I just said it in words. Let's write that down so that we are very, very clear on what's happening here. Let me continue using blue, but I'll go to the marker. For current, we're going to be able to say something right away, just reasoning this out. We said that all of the current comes out of the battery, and some of it splits off, goes to R1, and some splits off and goes to R2, and the rest goes to R3. So if we add up 1 plus 2 plus 3, then we're going to get the total current. Think of the current from the source as like the total, and this is huge. Current from the source, or the total, is equal to current through resistor 1 plus current through resistor 2 plus current through resistor 3, and really I should do the dot dot dot, right? Because any number of resistors in parallel will add up to give you the total current. All right, that's a very important relationship, and we really have started to answer this first question already, haven't we? We got the current kind of figured out. That's pretty cool. Now, what's coming next? Well, we're gonna go back to Ohm's law, and you'll see why. We're going to deal with voltages and also eventually end up dealing with resistances. Well, Ohm's law, if you recall, in general, was V equals IR, or current equals voltage divided by resistance, right? And actually, this is the form we're going to use. It's also my preferred way of writing it. Don't worry about that. That's what we're going to look at. And you'll see why. It's going to take us a couple steps to get there. Let me rewrite this. Current is equal to voltage divided by resistance. That's Ohm's law right there. So, but let's get specific with this. If we think about this, we have a current that is sort of like the total current. If I just kind of think of all three of these resistors as one thing, we have a total current flowing out of the battery and flowing back to the battery. And that's the current of the source. Add a little S right there. We have a voltage gain supplied by the battery, and overall we have a voltage drop supplied by the resistors. Now we're not going to yet see how that's all arranged, but there is a total voltage here, so to speak, and so I'll just put an S because it's equivalent to the voltage of the source. Now the resistance. I'm going to write an EQ, and just like it was with series circuits, I'll put this over here. Really, REQ equals what's called equivalent resistance. In quotes there, just a little thing off to the side. So it means that if we consider this circuit and these three resistors as one thing, then they combine somehow to make an equivalent resistance. And it's that equivalent resistance that will determine how much current flows through the circuit. So, REQ. But I want to write a few other Ohm's law equations because there's something really cool going on. I have a resistance of R1, I have a voltage drop across resistor 1, and I have a current through resistor 1. Does Ohm's law work locally here? Absolutely does. Yes, it does. So I can also write the current through resistor 1 is equal to the voltage drop of cross 1 divided by the resistance of 1. I can also write the current through resistor 2 is equal to the voltage drop of across resistor 2 divided by the resistance of resistor 2. And same thing with resistor 3. And the same thing for any number 3. Any number of resistors hooked up in parallel. So I have these relationships that Ohm's law provides for me. Very cool. There's something else though. This thing I've already figured out about the current. I'm going to come back to this. This is interesting. I can rewrite this and then do a few things to substitute in, because you might see right away, or at least very easily, what's going to happen. Look at this. I've said already that current is voltage divided by resistance, right? Each of these is a current. Instead of writing a current though, instead of each I, couldn't I write a V over R for each of these? Watch. That's how this works. Back here. So let me rewrite this just so it looks like we're starting from the beginning. And I'll stop at 3. But instead of the current through the source, or I could also say instead of the total current, I can say that total current is equal to voltage of the source divided by equivalent resistance. Voltage of the source divided by equivalent resistance. And I'm going to continue writing the equation. So current through resistor 1 is V1 over R1. And I'm going to do current through 2, V2 over R2. You see what's going on. So for current 3, I did the same substitution that was written here. But there's one more interesting thing, and this may not be quite so obvious. And it comes back to looking at this. So check this out. We haven't said this yet, but it's important. If we sort of ignored these two other resistors and said, well, we got one resistor hooked up to our battery. The battery provides a voltage gain. This resistor provides a voltage drop, yes? Now let me ask you this. If I add another resistor, does that change the voltage gain from the battery? Well, no. And so this remains unchanged. And there's something else also. You look at this and you can trace from this resistor right back to the voltage source with not having to go through anything else. Same thing here with R2. You can trace right back to the voltage source without having to go through R1. And the same for R3. Trace right back to the voltage source without having to go through the other resistors. What's interesting about that is that means that R3 and R2 and R1 each see the same voltage difference here. Now it's a gain here and it's a loss here, but it's the same as that. This is another important relationship that I need to make sure I write down. Voltage of the source equals voltage of drop of R1, which equals the voltage drop of R2. This is different, which equals the voltage drop of R3, which equals however many resistors you've got. So we've also now said something about the voltage and how voltage works in a parallel circuit. If you can trace from that resistor back to the source without going through any other component, then the voltage drop is the same as that voltage gain. Has to be. It just has to be. And so we see this, and this is different than what we saw with the series circuit, isn't it? And well, this is different also from series. Okay, but we're going to use this relationship now. Remember, we're working over here, right? We're trying to say something about, really about resistance now. It's the only part of the question, the original question, we have not answered. We talked about voltage, talked about current. How does resistance work in parallel circuits? Well, I can see resistances and the equivalent resistance, and that's brilliant. So, but how about these V's? I got to try to get rid of them. Well, the cool thing is with this relationship, I know that V1 equals Vs, and it also equals V2, and all these V's up here are equal to each other. So I'm going to rewrite this one more time, and I'll just use Vs for each of these because it's the same as those. It's equivalent. So Vs R1 plus Vs over R2 plus Vs over R3. And now that I have Vs in every term, I could divide the whole thing by Vs, and Vs completely cancels out. And you might say to yourself, oh, well, Mr. Woods, that just means that the equivalent resistance is R1 plus R2 plus R3, just like it is with series. Well, what you're saying is that equivalent is R1 plus R2 plus R3 for a parallel circuit, because that's what it also is for series. But the problem is, mathematically, no. We didn't get here by canceling out those V's, those voltages. What we got, when you cancel something out, there's a 1 in its place. We got this. 1 over the equivalent resistance equals 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. And now that's a bit awkward. What I could do is take the number, invert it, and invert it, and invert it, and then add them. But then what I have to do is invert my answer. And so really, you sometimes see it written this way, but you also sometimes see it written. So the equivalent resistance is perfectly plain. It's not inverted. It's not the reciprocal. But you can't just flip each of these and go, oh, that's just R1, because you end up with this. And that's just R2. No, you end up with this. No. If you flip this side and then you flip this side, you flip the whole side at once. Boom. R1 plus 1 over R2. That's 1 over R1 plus 1 over R3, right? And you can't just say, well, this is the same as that. No, it's not. Mathematically, they're different. And so this is pretty crazy here. Either way you write this is accurate. It's fine. But if you actually go to solve for the equivalent resistance, you want to keep track of things, write things down carefully, and you'll get there. The math is simple, even though this looks like a mess. It's just fractions. It's just fractions. Now, that's pretty cool. But what does this mean for us? Watch this. We have to say a couple statements, and then we'll wrap this up. Because, all right, rewrite it here for you one last time. I'll do the plus dot 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 just in case. So what happens if you add another resistor in parallel? Let's say we added an R4. Then what we're doing is we're making the denominator of this fraction larger. If we add an R4, then everything here in parentheses gets larger. That's the denominator. And that means the overall value gets smaller. So, adding a resistor in parallel, what does that do? Does that increase or decrease the equivalent resistance? It decreases the equivalent resistance. And if the equivalent resistance decreases, then what happens to current? Will current increase or decrease? Less resistance, more current. Current will increase. And so, real important to keep that in mind. And that is totally opposite of a series circuit. In series, if you add a resistor, the equivalent resistance increases and the current decreases. Here, in parallel, the equivalent resistance decreases and therefore the current increases. What is that like? You ever go grocery shopping? And this guy's kind of bored, right? You go to a store and they have all these checkout lanes, and only one of them is working. And the line for that checkout line is like wrapping around the store, and it's people are eating their food while they're waiting in line. It's ridiculous. What do they do to make their customers happy? They open another checkout lane. So they add in parallel to the first one a second spot, and this is a spot where someone has to slow down as they get out of the store. It's a resistor. It slows the flow of people. However, by opening another checkout lane, they get everyone out of the store a little bit faster. If they open a third one, they get everyone out of the store even faster. So by adding resistors in parallel, you will increase the flow through that circuit. The grocery store is a great analogy for parallel circuits. That's it for now. Thanks for watching. I'll catch you next time.